How does a neural network hold a memory steady for hours, yet instantly switch thoughts the moment the context changes? This paper explores the mathematical architecture that balances stability and flexibility in sparse neuronal networks. To solve this riddle, we must look at how networks maintain a state called marginal stability. The authors investigate how biological structures force neural networks to sit right on the edge of instability, allowing them to hold data without getting stuck. Building on this concept, the researchers observe that trained recurrent neural networks are not random, they develop specific structural features. They model this using a sparse Jacobian matrix that accounts for the fundamental differences between excitatory and inhibitory neurons. To understand the dynamics of this structure, the authors treat the Jacobian as a large random matrix. By applying a supersymmetric method, they analytically derive the exact boundary conditions that dictate whether the network stabilizes or effectively behaves chaotically. This analytical approach reveals a striking geometric shape in the eigenvalues as shown here. The fast excitatory neurons collapse onto the real axis, creating a stable bar, while the inhibitory neurons form a circular blob that governs the network's flexibility. The power of this framework is its precision. It accurately predicts the spectral shape observed in networks trained on memory tasks. Importantly, the authors show that their formula works for sparse matrices, generalizing previous theories that were limited to dense connectivity. Ultimately, this research highlights that slow heterogeneous inhibition is the primary driver of functional stability. This configuration makes the network naturally robust, allowing it to perform complex tasks without requiring the synaptic weights to be perfectly fine-tuned. This work bridges the gap between biological observation and statistical field theory, explaining how chaos and order coexist in the brain. For more lightning talks on neural network theory, visit emergentmind.com.